Good afternoon, colleagues, and happy Engineering World Day. My name is Katiso Mkwena, a chairperson of CESA YPF Free State and a civil engineer with Beacon Group. I am honored to be your facilitator for today's session in our World Engineering Day webinar series. Our theme for 2026 just gonna move my slides slightly. We would like to firstly thank our 2026 annual YPF sponsors for their continued support, especially our diamond sponsors, Pufanikiwe and Zutari, our gold sponsors, and our silver sponsors. Our theme for 2026 is World Engineering Day for Sustainable Development. We started this with the first webinar delivered where there was a delivery of battery energy storage system that was done by WSP. And then this is our second webinar by Zutari, which is N1 Sinkholes. Please meet our panel of speakers. The first speaker that will be speaking to us is Savannah. Savannah Canto. She's actually a geotechnical engineer at Zutari. She has over 5 years experience in civil engineering projects in Africa, Middle East, involving foundation design, retaining structures, slope and stability, ground improvement projects. She also holds a BH honors in geotechnical engineering from University of Pretoria. On SANRAL N1 Sinkhole Rehabilitation Project, she was based on site as an assistant resident engineer supporting construction and supervision of geotechnical works. Our second speaker is Anemi Swart, a civil engineer at Zutari, based in Pretoria, specializing in geotechnical road designs, road safety. She has over 15 years experience delivering large-scale transport infrastructure projects across Africa, Australia, and Middle East. On SANRAL N1 and R21 Sinkhole Rehabilitation Project, she served as assistant resident engineer, supporting construction supervision of traffic accommodation and roadworks. I will then give it to our first speaker, which is Savannah Canto, to actually do the presentation. Savannah, up to you. I'll just send this to you to start the presentation.
Thank you, Katiso. I will share my slides. It says I need you to disable your sharing so I can share. Thanks. Okay, are they showing in presentation mode? Yes. Can you see? Okay, great. Thank you. Morning, everyone, and happy World Engineering Day and month. So today, my colleague Anami and I will be presenting on an interesting project that we were a part of, the rehabilitation of the sinkhole on the N1. And we'll go through a background and the design solution for the project, and then take everyone through the construction process and describe how incorporating technology led to a very efficient design and construction process. So first and foremost, we would like to acknowledge and thank everyone involved in making this project a success. So firstly, our client, SANRAL, thank you very much for the opportunity for us to work on this project. And then to the design and site supervision teams at Zutari, as well as to the contractor, Jordan Construction, and the geotechnical subcontractor, Terra Strata. And also a huge thank you to CESA for letting us present today. and to the CESA Aon Engineering Excellence Awards for selecting our project and for being a wonderful platform for consultants to showcase their projects. So firstly, some background on the formation of the sinkhole. So the sinkhole formed in January 2022, just after the flying saucer interchange on the verge of the N1. And Zutari was responsible for the design and supervision of a remediation solution. So this shows some drone imagery of the sinkhole, and you can also see the wider crack pattern around the sinkhole. Here's some more images of the crack pattern surrounding the sinkhole on the inner 2 or 3 lanes of the highway. So we started with an initial geotechnical investigation to find out more about the ground conditions surrounding the sinkhole. So you can see those mounds on the road are where boreholes, percussion boreholes were drilled to obtain more information on the ground conditions. And these showed that there was very poor subsurface conditions with a lot of cavity areas. And one thing was that we couldn't do any excavation. We couldn't do any investigation too close to the sinkhole because it wasn't safe to access at this stage. So our investigation was limited to the surrounding area that we could access. And this shows roughly the size of the sinkhole. So it was around 16 by 80 by 8 meters in size. And then we used a drone to enter the sinkhole and get this cross section so that we wouldn't compromise any safety. And the depth of the collapsed area from the surface was about 5 meters. So between Centurion and along the N1 and R21 route, there's a lot of dolomitic terrain. So this is showing the location of the sinkhole in terms of the dolomitic geology in the area. So the dolomite is all the blue on the map. And this is just a brief introduction to sinkhole formation. So they are formed on dolomitic terrain. So what happens is that over many years, there will be cavities forming within the dolomitic bedrock due to dissolution of the dolomite from factors such as acid rain. So these cavities sometimes remain stable beneath the earth, but when there's a change, for example, from lowering the water table and a pipe leaking or some leakage at the top that causes the fines above to wash into the cavernous areas, then the bridge of stable soil above basically gets eaten away at until it can no longer support the loads above, and then a sinkhole will form. So onto the design solution. There were basically 2 main solutions considered, or 2 aspects that were targeted. So firstly, we had to repair the immediate area of the sinkhole. So to do that, we needed to use a vertical retaining wall because it was important that the road remained open to traffic, and a full closure of the N1 would not have been economically feasible. So in order to keep some of the lanes running and save space, we couldn't do a battered excavation, and therefore we needed a vertical excavation. So the only way to achieve that was to install a piled wall surrounding the sinkhole and then to excavate the sinkhole area and then clog the throat of the sinkhole. And further to that, a wider area was improved through compaction grouting, ground improvement. So on this grid, each point on the grid shows where a borehole would be drilled for compaction grouting. So that would involve drilling boreholes we chose to about 30 meters depth and then pumping in a compaction grout mixture under pressure along each meter of that borehole to fill any voids or cavities underneath the highway. And the next slide will show a section through this piled wall. So here we can see a section through the piled wall. So for the piles, we used Odex piles. They're steel piles with a casing of 12 millimeters. And these were selected because the dolomitic geology is very variable. So it's variable in terms of the depth to bedrock. The bedrock profile is very variable, and there will also be large boulders of dolomite, sometimes loose within the residuum, that need to be drilled through. So the retaining wall was formed of these Odex piles that were installed to a depth of 25 meters. And then lateral support in terms of self-drilling ground anchors were used to keep the wall in place. And then this allowed us to excavate in stages the sinkhole area. So how it would work is the piles were installed and then a row of anchors was installed with each excavated layer. And we excavated in lifts of 2.5 to 2 meters at a time. So the idea of excavating is then to reach the throat of the sinkhole, which was expected to be around 15 meters depth, and then to clog that throat and then install it, geogrids and an engineered fill, and then reinstate the road. And because of some safety concerns and more information that we received on the ground conditions while we were excavating, we deviated from the standard inverted filter method to repair the sinkhole and instead compaction grouted from within the excavation, which I'll explain in the construction slides. And now over to Annemie to explain some of the traffic accommodation and pavement aspects.
Thank you, Savannah. So on the pavement slide, the roadworks involved the reconstruction of approximately 97 meters of primary pavement area, shown there in orange in the image, which had been significantly damaged by the sinkhole. The excavations required for the sinkhole rehabilitation is indicated with that yellow hatched area. The primary objective in this zone was to remediate the sinkhole and provide structured support to the road throughout the construction process. In the secondary pavement area, indicated in blue, extending over approximately 280 meters, rehabilitation was required following the completion of the planned grouting works. So on the next slide, this cross-section illustrates the proposed layer works within the primary sinkhole area, as indicated by that orange hatch in the top right image. The red hatch in the cross-section highlights the temporary road widening required to accommodate the two-phase traffic accommodation plan. The pavement reconstruction for both the sinkhole area reinstatement and the temporary widening comprise a natural gravel selected layer, a cement stabilized subbase layers, a bitumen treated base, and a 50 millimeter asphalt surfacing. A glass grid geotextile was proposed between the BTB layers to promote a uniform riding surface and mitigate potential differential movement. On the next slide, following completion of the grouting works, the initial plan for the secondary pavement area, completion of the sinkhole works, the initial plan for the secondary pavement area after completing the grouting, you can see that area is highlighted in blue in the top right image, was limited to milling, crack repair and sealing with a 50 mil BTB rubber gap graded asphalt surfacing, as reflected in this cross section. However, grout-induced heave required a revision to this original pavement design. You'll see on the next solution illustrated, the previous one, Savannah. Thank you. So in this cross section, you can see the partial reconstruction of the pavement that we ended up with, including milling and crack sealing, followed by the incorporation of varying thicknesses of BTB as required, reinforced with glass grid and a 50 mm asphalt surfacing layer. This approach restored both the structural integrity and ride quality of the affected area, while minimizing program delays and associated traffic impacts. On the next slide, concerning accommodation of traffic, you can see here a two-phase traffic accommodation plan was implemented, comprising A outer and phase B inner work zones. This that 4 lanes remained open during peak traffic periods. This image shows the phase A work zone, with traffic accommodated on 4 narrowed inner lanes. The only exception was a 2-week period during casting of piles closest to the traffic, where only 3 lanes could be maintained. This duration was reduced from a planned 4 weeks, representing a significant program gain of 2 weeks. On the next slide, this image shows the phase B inner work zone, where traffic was redirected to the 4 narrowed outer lanes to allow construction activities to proceed within that intersection. And then on the next slide, a brief phase C was introduced to widen the phase B work zone and complete that final tie into the phase A works, thereby minimizing our overall disruption to the road users. On the next slide, our Google Earth image shows phase A of traffic accommodation plan in plan view relative to the sinkhole area indicated in orange. To accommodate the required excavation and ground improvement works, the 6 through lanes were reduced to 4 narrowed inner lanes, excavation and ground improvement works. And then with phase B on the next slide, where traffic was diverted to the outside lanes, maintaining 4 narrow through lanes, while enabling ground improvement works within the inner work zone. You can see also there in the right bottom image, through grouting on the predetermined grid Savannah was earlier speaking about. And then on the next slide, due to limited space on the southbound carriageway for the proposed traffic accommodation, it was necessary to temporarily widen the N1 southbound carriageway. This ensured the availability of 4 through lanes at all times during the construction process. The widening area is marked with a blue hatch, necessitating a slight realignment of the original gravel side drain. The drain was lined with concrete and integrated into the stormwater system located further downstream. That brings us to a couple of slides we'll share with the construction, and Savannah will first be taking us through some of the geotechnical slides. Thank you, Savannah.
Thanks, Anami. Okay, so before the piling could start, we had to establish a safe working platform for the piling rig. So dynamic compaction was used to do that. And here's a picture of the dynamic compaction works before the piling started. And this shows some images from the commencement of the piling, which started in October of 2023. And the ODEX piles that we used were 610 mils diameter. And there you can see the drill bit and the hammer for the piling. And with each meter of piling, sample was taken from the drilling. So that sample was then logged to give us a picture of the geological conditions that we would see as we unearth the excavation. And all the piles were tied together at the top with this strapping beam that you can see on the right-hand side image. And here's an aerial view from one of our drone surveys. And you can see the piled wall starting to take shape as the piles are being installed. And this shows the geology across the face of the piled wall that was obtained from logging the percussion drilling, percussion chips. So the brown material is mostly fill that was used for the original road embankment. And then the yellow color is the dolomite residuum, and the red is also a residuum of dolomite, but it was WOD material. So that's like a very light compressible material that's black in color that I'll show in some of the images. And here you can also see the variable bedrock levels of the dolomite. So you can see the pinnacles, which is raised portions of the dolomite bedrock. That's all in the gray colors. This shows an aerial image of the wall once all the piles were installed and we were ready to start excavating. So this is the first lift of the excavation. We went down 2.5 meters approximately and then installed a row of anchors. So the anchors, I think the upper row was they were 28 meters long with a 17-meter fixed length, and 52 diameter bars were used. And there you can see in the left image the road layer works. That was mostly the full material for the road. And then the left image shows the shotcrete that was applied to the face. And the right-hand side, you can see the anchors that have been pre-stressed. So after the first lift of anchors was in, then we could move on to the second lift. And here you can see some of the black colored WOD material that I spoke about earlier. And here's some views into the excavation. Sorry, it's shifting. So you can see the variability in the dolomite profile. So there were some pinnacles unearthed in the excavation, which posed some challenges because dolomite rock is extremely hard. So we left them in place where we didn't need space to work, and then where we needed space, we had to either pick the rock away or drill it to weaken it and then remove it. So this is once the second lift had been completed, a view into the excavation. Also a view from a ramp at the top. You can see how close the cars or the highway is in the background. Here are some images from the third lift where you can see more pinnacles being unearthed in the excavation. And there on top of the road, you can see one of the drilling rigs for grouting on the road surface, busy drilling a borehole. And this slide just illustrates how valuable it was to log the chips from the piling, because it gave us an idea of what to expect in the excavation, and also to know whether, when we hit rock, whether it was a dolomite boulder, for example, that needed to be removed, or whether we had hit the dolomite bedrock. So here you can see in the image on the left, it's a dolomite boulder, which they call the dolomite floater, unearthed in the excavation, and that was identified as a boulder because in the logging you could see that it was isolated within the WOD material. While we were doing the third lift of anchors, there was an additional subsidence, so a small sinkhole formed within our excavation that you can see on the right-hand side. So once this happened, we had to verify whether it was safe for working. So we consulted with our D4 dolomite expert, and we eventually filled this with grout to continue working. So here's some more pictures of that subsidence. So once that was filled, we continued with another lift in the excavation. And once we got to the fourth lift, we also started seeing some of the grout from the road sometimes enter the bottom of our excavation. So that gave an idea of how interconnected the karstic pathways were beneath the ground. So we became concerned about the ground conditions beneath us. So we ended up doing some exploration drilling within our excavation area to get a better idea of the ground conditions. And this revealed quite extensive cavity areas below the excavation and also a deeply weathered feature below the initial sinkhole area, which was likened to be the origin or the source of the sinkhole where all the stable soil had washed into. So upon seeing that, instead of excavating further and trying to choke the throat of the sinkhole, it was decided to instead do compaction grouting from within the excavation floor to fill up any voids and cavities beneath the surface and in essence choke the throat of the hole through compaction grouting. So these are some images of the grouting operations within the excavation. And this 3D rendition shows our excavation and the subsidence that occurred while we were excavating. So you can see that the sinkhole formed between these two pinnacles of dolomite. And below that, there was a very deep weathered feature where all the fine material above could wash, which we then choked with the compaction grouting. So this shows some of the grouting results from grouting within the excavation along that weathered feature. So you can see, for example, the numbers in black. Those are the cubic meters of grout that went into those boreholes. So some boreholes were within excess of 1,000 cubes of grout. Here's some more images of grouting within the excavation. And then this summarizes the largest intakes of grout we had beneath the sinkhole zone. So in summary, or to emphasize how much it was, an Olympic swimming pool has a volume of 2,500 cubes. And that's almost as much as went into these three holes highlighted in yellow. So that just shows the extent of the problem that was existing there. So once we were satisfied that it was sufficiently grouted, we applied geotextiles to the base of the excavation to ensure that the platform would be stable to build up on and for extra support and stability for the future. And we could then fill the excavation with engineered fill so that the roadworks could be reinstated. So these are just some pictures of the filling exercise. And while all that was happening, there was the ongoing compaction grouting occurring on the road. So this just shows the drilling of the boreholes and then the grouting apparatus. So for the compaction grouting on the road, it would be a 30-meter hole that was drilled and then a casing was installed. And every meter grout would be pumped in under pressure until certain cutoff criterion in terms of the pressure or the volume of grout were reached. So we would keep track of the grout intake at each borehole and work with the contractor on deciding which secondary boreholes would need grouting. So initially a primary grid was done, and then where grout takes were large, additional boreholes were drilled and grouted at a split spacing within the primary holes. And now Anumi will take you through some of the challenges experienced during the grouting.
So thank you, Savannah. The compaction grouting on the road caused unforeseen challenges in some instances, where the grout resulted in heave on the N1 traffic surface. Ground heave incidents resulting from the grouting operation were managed through a combination of risk workshops, temporary line closures, and prompt milling and patching interventions, as shown in that image to the far right. The image on the left shows an example of a visible crack that developed in the outer work zone due to those grouting exercises. Another is the 110 mm high bump that formed in the southbound carriageway due to ground heave, visible in the middle image. To mitigate the risk to the travelling public, it was very important. To do that, we implemented daytime slow lane closures outside of peak traffic hours to minimize the potential impact of any future heave on traffic. The next slide, the image in the center shows a 3-meter excavation conducted to investigate whether the grout pressure could be relieved in this case where a heave occurred. No grout was found, suggesting that the grout likely lifted approximately 15 meters of material, which corresponds to the depth at which grouting was being carried out at the time. Following this incident, slow lane closures were implemented during the day to mitigate the risk of future heave impacting traffic. The next slide shows a summary, summarizes the complete grouting works, including the total grout volumes used. When combining the volumes for phase A, noted down there, and phase B, as well as compaction grouting within the excavation, the total grout volume equates to approximately 9 Olympic-sized swimming pools using our Olympic swimming pool comparison. That is also equivalent to around 3,800 concrete mixed trucks, mixed truckloads of grout. On the next slide, the following images illustrate pavement and roadworks construction activities carried out during phase A, following the repair of the sinkhole. So on the next slide, those images show the mixing of the cement stabilized material, and also the following slide in preparation for placement of the sub-base layer. On the next slide, these images show pavement rehabilitation, yes, for the section over the excavation hole and the temporary road widening. A cement stabilized sub-base was installed in both areas. In the image to the right, the grade is spreading and shaping the cement stabilized material, trimming the layer to the correct levels and crossfall, and preparing the surface for compaction. On the next slide, you can see milling operations that's underway to rehabilitate areas where grouting activities have disrupted the road surface. The next slide, bitumen-treated base layers have been placed with coring undertaken to verify in situ density and layer integrity. Hamburg core samples were extracted for performance testing. A glass grid geotextile GG100 was installed between the BTB layers to provide reinforcement and mitigate reflective cracking. On the next slide, asphalt construction is in progress over a pavement structure comprising bitumen-treated base layers with a glass grid geotextile installed between the BTB layers. To expedite the construction program at SANRAL's request, the originally specified G1 base for the primary pavement area, where the sinkhole rehabilitation was undertaken, was replaced with a BTB base and medium asphalt surfacing. On the next slide, this was followed by the application of pre-coated chips onto freshly placed asphalt surfacing to enhance surface texture and skid resistance, followed by rolling to ensure embedment. The next slide shows phase A prior to opening and just prior to moving over to the inside lanes, which is the phase B work zone. So on the next slide, you can see the phase B work zone. And the following images just illustrate pavement and roadwork construction activities carried out during this phase B following the completion of phase A. So this drone footage taken in early August of this year, of 2023, offers an overview of the site after the excavation will have been backfilled and the outer section of the southbound carriageway has been repaired. On the inside of the southbound carriageway, the work zone has just been established. On the next slide, you can see after completing grouting and pavement rehabilitation in that outer work zone, the grouting process proceeded in the inner work zone. And you can see them starting to work there. The next slide, upon completion of the ground stabilization works, milling of the existing pavement layers, sorry, it's still, yes, thank you. Milling of the existing pavement layers commenced in accordance with the specifications. This image shows milling to a depth of 50 millimeters. The next slide shows also night works that was implemented to maintain a tight construction program. Then milling from 50 to 150 millimeters on that slide. And then the following slide, BTB was placed over the existing G1 layer. Next slide shows the sorry,
the slides are jumping around. Is it this one you need?
yes. Yeah, so that's just the BTB layer over the existing cement stabilized layer. And then a glass grid geotextile and second BTB layer were placed over the existing cement stabilized layer. And then on the next slide, you can see the placing of asphalt. And then after that, the chips have been placed. This is just the previous slide is just the pre-marking of the line markings that you can see there. And then the opening of the first two lanes. Opening up of the fourth lane. And then finally on the last slide of the construction photos after 12 months of construction compared to the original 24-month program, the road was successfully opened to the public, where the contractor not only met, but significantly exceeded their CPG targets. So that's all the construction photos. I would quickly like to dive into some of the technology that was incorporated into this slide.
We stop sharing so you can access it.
Okay. Be there in a minute, thank you. Okay. Can you see my screen?
Not yet.
Yes, we can see incorporating technology.
Fantastic. Okay, so the use of advanced technology played a critical role in the effective planning and management of the project. As part of our design approach, we actively integrated advanced technologies to enhance understanding of site conditions and inform engineering decisions. In this project, the gravimeter was utilized during the initial phase to provide valuable insights into the underlying subsurface conditions. Zutari's advanced drone survey equipment played a crucial role in supporting on-site design and decision-making by facilitating accurate quantity verification and providing high-resolution survey data to support informed on-site design decisions. The drone imagery was also hosted on a Geoverse platform, enabling the creation of 3D snapshots snapshots in time at various stages of the project. This proved invaluable in numerous instances for tracking progress and supporting decision making. And I think before we proceed, I would just like to quickly share this GeoVerse. Oh, I see it closed. It closed on this side. I will get it up before the end of this slideshow. But each and every of these dates presents a 3D presentation of the drone footage that has been taken, and you can literally in 3D move to any point on that site, which was really very valuable. Last 3D modeling and PDF creation proved highly effective in visually communicating specific areas for discussion and decision making to produce a workable, resilient solution. I would just like to thank CESA for the opportunity to present this project and providing a platform where engineering excellence can be shared among consulting engineers across South Africa. We also extend our sincere appreciation to all parties involved, our client, SANRAL, the Zutari supervision team, Joden Construction as the main contractor, and TerraStrata as a subcontractor, for their contribution to the successful delivery of this project. Thank you, and I'd like to give some opportunities for questions and answers at this point in time. Thank you.
Thank you so much, Anim and Savannah, for that incredible insight breakdown. It is clear why this project was recognized for excellence. We will now open the floor for our question and answer session. But before we actually allow our delegates to actually type their questions and answers in the chat box, question and answer chat box, I'll actually just ask these few questions that I prepared for you. The first one is, what were the lessons for future infrastructure resilience that were learned from this project, and what were the most critical geotechnical investigations and engineering methods you used to understand the extent of the sinkhole and design of safe and lasting rehabilitation solution? The third one is that what were the biggest engineering or environmental challenges you encountered during the rehabilitation, and how did your team overcome them?
Thanks, Katiso. I'll take the first one about the critical geotechnical investigations and engineering methods to understand the extent of the sinkhole. So I would say in the initial investigations we did a gravity survey, and then to verify what we saw in the gravity survey, we did drilling of some percussion boreholes, and then that gave us an idea of where the problems lay. But due to the fact that we had limited access at the beginning, it was also very valuable for us to keep track of all the information that we received during the construction process. So even during the grouting process, for the example, when we were drilling percussion boreholes for grouting, all of those were also logged geotechnically to give us a wider understanding of the conditions in the area. So it was important to also keep a ongoing look at what insight the additional construction information gave.
Yes, I think, sorry?
No, thank you. Yes, you can proceed. I'm not sure if you can see the answers in the Q&A chat box.
We see these three questions from Godfrey.
Yes. Okay, I'll just read the other one for you. So the crowd worked too well and created heave, or did you suspect it will happen? Does that indicate that toxic mode was isolated and will not spread later on?
So if I can jump in, you can add on, Savannah. That was not necessarily expected. But once it was picked up, obviously we had that risk workshop to understand why it is happening, because as you could see in one of those images, it was occurring from quite deep depths, and we had to sort of first isolate the problem, understand where it's coming from. So there was a couple of options where it could be coming from, and then obviously mitigating the risk to the public. So one of the mitigations that we also implemented, apart from the road closures, was also to have watchmen to monitor visually any heave that starts occurring, watching out for that. And then also survey measurements was taken daily to pick up any potential movement on the surface. And then obviously the response system had to be in place to quickly act on any heave that does occur, and that does occur in the southbound carriageway. I must say the closure next to the work zone that we did outside of peak traffic hours did prove very valuable, as we did have heave occurring in those closure zones, and so that really proved very valuable to have done that and mitigate that hazard to the public. So if that answers your question, I would just maybe go back to the environmental challenges question you also posed. So let me jump over to the environmental question. There was a lot of environmental challenges, and specifically with it also being a dolomitic area, it was very important to limit any water infiltration into the sinkhole area and surrounds. So we had to keep a very watchful eye on that and make sure that any water leakages or and I'm going towards grouting works, and all of this is dealt with in a very careful way. So with grout and those works, to limit that from getting into the stormwater system, we had to also implement some mitigations. So we ended up providing sand traps to ensure that any grout effluence is absorbed in those sand traps instead of ending up in the stormwater system. Yes, so that's on the environmental. That was very important.
Then the second question is that, did the project make a loss because of UF or drone surveying? Was it challenging to get the drone information and processing it all on the new software? Did this cost the project, or was the client happy to pay for all the additional services?
No.
That's the second question.
No, that's something we do as a standard across all our contracts. It's not additional, so it's easy to extract, and we have all the software for that. So no, it's not the additional cost. It's part of our services that we do. Our digital team goes from project to project and picks up the drone imagery and loads onto the Geoverse. And I must say, it where there's conflict points, it's always very valuable to go back to that. And where there's concerns that are all unsurety about quantities, it's also very, very valuable. So no, it's not a difficult thing to import. It's something we do every day. Yes.
Okay, thanks. Let's move to the next question. Wouldn't it have been cheaper to just build a bridge instead of all excavations and backfilling?
Savannah, I'm not sure whether you want to take that one. I know that was one of the options considered.
yeah, there was an economic analysis done, and this was selected as the most feasible solution.
The last question that I'm seeing is that were the piles and the cars around the sinkhole left there? Yes, yes.
Could you repeat it?
Yeah.
Yes, were the piles and air cars around sinkhole left there?
Oh, I see. Okay. The piles were left in place, but so they were installed, they were cut at a certain layer so that at a certain level so that the roadworks could be reinstated. So I think it was 2 meters below the top of the pile that they were cut.
Okay. And then the other question is that do you have an idea of the current conditions and the performance ever since the repair work, and if maybe other cracks formed out elsewhere outside of the repair area?
It seems to be performing well. I've driven the road a few times since construction has been completed, and it seems to be in good condition. Anami, do you have any?
Ironically, they actually built a church on that sinkhole itself. So that seems to be performing quite well at this point in time still. But also the rest of the road's condition, yeah, to my knowledge also it is very good. Yeah.
Okay. And then the other question is that what went wrong to the initial geotechnical soil investigation prior to the construction of the road?
So I'm not sure what was done for the initial investigation many years ago before the road was built, but the main cause of the sinkhole was a drainage problem. So basically water inflow from the drain on top caused the sinkhole. So something was not necessarily wrong in the initial investigation. It might have been stable if there hadn't been a drainage issue that resulted in the sinkhole.
And I think the last question is that were the piles designed as end bearing or friction or both?
Just come again with a question, please. Well,
Were
Yeah,
the piles
friction.
designed as an end bearing or friction or both?
We didn't consider end bearing really because we were not sure about the rock layers, the rock dolomite depth, and because it's very variable. But yeah, we just checked the embedment was deep enough for the planned excavation depth. So it wasn't a traditional pile design for a structure. It's just for the retaining wall. Yeah.
Okay. Okay, how did you eventually mitigate the heaving during the pumping of the ground? That's another question.
So
how did we?
mhm.
No,
Yes.
you go
Oh, it
ahead,
said that
Savannah.
how did you eventually mitigate the heaving during the pumping of the ground?
Oh,
To
you can go.
control the issue of the heaving, we had that lane closure, and then we also had people watching as we were grouting and smaller tolerances for movement. And there was also a cutoff at a certain depth below ground level where we reduced our pressure criteria for the grouting. Don't know if you want to add, Anami.
That's pretty much the essence of that.
With that, I just wanted to just tell everyone that this is recorded and it will definitely be posted and be shared on CESA YouTube page called CETV for everyone to access it. And as we actually wrap up, I want to extend a massive thank you to Anemi and Savannah for sharing the technical rigors and success of the N1 Sinkhole Repair. It's actually projects like this that remind us that why we encountered this profession to provide safe and reliable solutions for our communities. I also again would like to actually thank our sponsors, our diamond sponsors, our gold and silver sponsors, and thank you for everyone who joined us today. Your engagement helps us keep our profession standard high and our industry connected. And on behalf of CESA YPF Free State, I have a wonderful and productive World Engineering Day. With that, in the absence of any other questions, I would like to officially close this webinar.